Close your eyes and imagine standing on Earth, looking up at the night sky. Stars scattered across the darkness like diamonds on velvet. Each point of light represents an entire sun, perhaps with planets orbiting around it. Some of those stars are just a few light years away. Others are hundreds, thousands, or even millions of light years distant. Now imagine leaving Earth, not in imagination, but physically, stepping aboard a spacecraft and pointing it toward one of those distant stars. How far could you actually go? How much of the universe could you explore in a single human lifetime? This question has fascinated humanity for centuries. We've dreamed of traveling to other worlds, of walking on alien planets beneath foreign stars. But dreams must eventually confront reality. And the reality of space travel is both beautiful and sobering. Space is vast, incomprehensibly, impossibly vast. The distances between stars are not measured in miles or kilometers, but in light years. A light year is the distance light travels in 1 year, moving at 186,000 miles per second. That's about 6 trillion miles. The nearest star to our Sun, Proxima Centauri, is 4.24 light years away. That means light, the fastest thing in the universe, takes over 4 years to travel from that star to us. If you tried to drive to Proxima Centauri in a car going 60 miles per hour, never stopping, never slowing down, it would take you 48 million years to arrive. Walking would take even longer, roughly 900 million years of continuous travel. Obviously, we're not driving or walking through space. We're using rockets, spacecraft, the fastest vehicles humanity has ever created. But even our fastest spacecraft are incredibly slow compared to the cosmic distances we're trying to cross. The fastest human-made object ever is the Parker Solar Probe, launched by NASA to study the Sun. At its maximum velocity, diving close to the Sun and using its gravity to accelerate, the Parker Solar Probe reaches speeds of approximately 430,000 miles per hour. That's faster than anything humanity has ever built. It could travel from New York to Los Angeles in less than 10 seconds. But even at that incredible speed, traveling to Proxima Centauri would take about 6,700 years. Far longer than recorded human history. Far longer than civilizations last. And Proxima Centauri is the closest star. Most stars in our galaxy are thousands or tens of thousands of light years away. And other galaxies are millions or billions of light years distant. So when we ask how far humans could travel in a single lifetime, we're really asking, what are the absolute physical limits? What technologies could we develop? What speeds could we achieve? And what would happen to a human body traveling at those speeds? The answers involve physics, biology, engineering, and the fundamental structure of space and time itself. We'll explore conventional rocket technology first, then more exotic propulsion systems, and finally, the theoretical limits imposed by Einstein's relativity. By the end of our journey, you'll understand exactly how far humanity could reach into the cosmos in the span of one human life. The answer might surprise you. It's simultaneously less than we hope and more than we expect. Let's begin with the reality of how we currently travel through space. Humanity has been traveling in space for just over 60 years. In that time, we've sent humans to the moon, placed stations in Earth orbit, and sent robotic probes to every planet in our solar system. These are genuine achievements, monuments to human ingenuity and ambition. But the distances we've covered are, cosmically speaking, almost nothing. The moon is about 240,000 miles from Earth. It took Apollo astronauts roughly 3 days to travel that distance. 3 days to cover a distance that light crosses in 1.3 seconds. That should give you a sense of how slowly we're moving compared to cosmic distances. The International Space Station orbits at an altitude of about 250 miles, traveling at 17,500 miles per hour. At that speed, it circles the entire Earth every 90 minutes. Astronauts aboard the ISS see 16 sunrises and sunsets every day as they race around our planet. But that speed, impressive as it seems, is only 0.026% the speed of light. If you pointed the International Space Station at Proxima Centauri and somehow gave it enough fuel to maintain that velocity indefinitely, it would take 175,000 years to arrive. That's longer than modern humans have existed as a species. The fastest spacecraft we've sent into deep space are the Voyager probes. Launched in 1977 to explore the outer planets, Voyager 1 and Voyager 2 are still operational, still sending back data from interstellar space. Voyager 1 is currently about 15 billion miles from Earth, traveling at roughly 38,000 miles per hour. At that speed, Voyager 1 will reach the distance of Proxima Centauri in about 75,000 years. It's not actually heading toward Proxima Centauri, just traveling in that general direction. But the math shows how long it takes to cover interstellar distances with current technology. New Horizons, the spacecraft that flew past Pluto in 2015, is traveling at about 36,000 miles per hour. Similar speed, similar limitations. These are among the fastest objects humanity has ever sent into deep space, and they're still painfully slow compared to the distances we want to cross. So why are we moving so slowly? Why can't we just build faster rockets? The problem is fundamental physics. Rocket propulsion works by throwing mass backward to push the spacecraft forward. Newton's third law. For every action, there's an equal and opposite reaction. The faster you want to throw mass backward, the more energy you need. And energy requires fuel. And fuel has mass, which means you need more fuel to carry the fuel, which requires even more fuel to carry that fuel. This is called the tyranny of the rocket equation, and it's one of the most frustrating constraints in space exploration. As you try to go faster, the amount of fuel you need increases exponentially. Eventually, you reach a point where the spacecraft is mostly fuel with just a tiny payload. Chemical rockets, the kind we currently use, are limited by the energy density of chemical reactions. The best chemical rocket fuels can achieve exhaust velocities of about 4 to 5 kilometers per second. That limits how fast they can accelerate a payload. To reach higher speeds, you need better propulsion systems. Systems that can generate more thrust with less mass. Systems that use energy more efficiently. Nuclear propulsion has been proposed as one solution. Instead of chemical reactions, you use nuclear fission or fusion to heat propellant and expel it at much higher speeds. This can theoretically achieve exhaust velocities of 10 to 100 kilometers per second, much faster than chemical rockets. Project Orion, a concept developed in the 1950s, proposed using nuclear explosions to propel a spacecraft. Small nuclear bombs would be detonated behind a massive shock absorber plate, and the explosions would push the spacecraft forward. Calculations suggested this could achieve speeds of up to 5% the speed of light, or about 9,300 miles per second. At 5% light speed, you could reach Proxima Centauri in about 85 years. Still a lifetime, but within the realm of possibility for a generation ship or long-duration mission. Project Orion was never built. The technology was too dangerous, too expensive, and politically unacceptable during the Cold War era. But it remains theoretically viable, a proof that nuclear propulsion could significantly increase our maximum speeds. Ion drives represent another approach. Instead of chemical or nuclear reactions, ion drives use electricity to accelerate charged particles to extremely high speeds. The thrust is tiny, just a gentle push, but it can be sustained for years. Over time, that gentle acceleration adds up to substantial velocity changes. NASA's Dawn spacecraft, which visited the asteroids Vesta and Ceres, used ion propulsion. Over its mission, the ion drive produced a total velocity change of 25,000 miles per hour, more than any chemical rocket could achieve with the same fuel mass. But even ion drives are limited by energy availability. They need electricity, typically provided by solar panels or nuclear generators. And while they're more efficient than chemical rockets, they're still far too slow for interstellar travel. The uncomfortable truth is that with current technology, or anything we could realistically build in the next few decades, humans cannot travel beyond our solar system in a single lifetime. The distances are too vast. the speeds we can achieve are too limited. Mars, at its closest approach, is about 35 million miles from Earth. With current propulsion technology, a trip to Mars takes about 6 to 9 months. That's manageable. People have spent longer periods aboard the International Space Station. Jupiter is much further, about 365 million miles at its closest. The Juno spacecraft took nearly 5 years to reach Jupiter. Saturn is about 746 million miles away, and it took Cassini nearly 7 years to arrive. These are the distances within our own solar system, and they're already pushing the limits of human endurance. Astronauts spending years in transit face radiation exposure, muscle atrophy, bone density loss, psychological stress, and numerous other health challenges. The outer planets are even further. Neptune, the most distant planet in our solar system, is about 2.7 billion miles from Earth. Voyager 2 took 12 years to reach it. Pluto, though no longer classified as a planet, sits about 3.7 billion miles away. New Horizons took over 9 years to get there, and these are still within our solar system. The edge of the Sun's influence, the heliopause where solar wind meets interstellar space, is roughly 11 billion miles away. Voyager 1 crossed it after 35 years of travel. Beyond that lies interstellar space, and the nearest star is 25 trillion miles distant. With current propulsion technology, the maximum distance a human could travel in a lifetime of, say, 80 years is perhaps 20 to 30 billion miles. That would take you beyond the heliopause, into interstellar space. You'd leave the solar system behind and venture into the void between stars. But you wouldn't reach another star, not even close. You'd spend your entire life traveling through empty space, never seeing your destination, dying in the darkness, with your goal still impossibly far away. This is the sobering reality of interstellar travel. With chemical rockets, nuclear rockets, or even advanced ion drives, we cannot cross the distances between stars in a human lifetime. We need something fundamentally different. We need propulsion systems that don't rely on carrying fuel. We need to tap into energy sources that allow for sustained acceleration over years or decades. We need technologies that currently exist only in theory and engineering studies, but they do exist in theory, and some of them might be buildable within the next century. Let's explore what those technologies could achieve. Imagine a spacecraft that doesn't carry fuel. Instead, it uses energy from space itself, or energy beamed from a distant source. A spacecraft that can accelerate continuously for months or years, gradually building up to a significant fraction of light speed. This isn't science fiction. These are genuine concepts being studied by physicists and engineers. They're not easy to build, and some require technologies we haven't developed yet. But they're theoretically possible within the laws of physics as we understand them. Let's examine several advanced propulsion concepts and calculate how far they could take us. Light has no mass, but it does have momentum. When photons strike a reflective surface, they transfer a tiny amount of momentum, creating pressure. This is called radiation pressure, or light pressure, and it's an actual physical force. Solar sails exploit this phenomenon. A large, ultra-thin reflective sail captures sunlight. The photons bounce off the sail, transferring their momentum and gently pushing the spacecraft forward. The thrust is minuscule, far less than even an ion drive, but it requires no fuel. As long as there's light, the sail provides thrust. Near Earth, sunlight provides about 9 newtons of force per square kilometer of sail. That's roughly the weight of a kilogram resting on your hand. Not much, but a sail covering several square kilometers can generate meaningful thrust, especially if the spacecraft is lightweight. The Japan Aerospace Exploration Agency successfully demonstrated solar sail technology with their Icaros mission in 2010. The sail worked, providing propulsion as predicted. NASA's LightSail 2, launched in 2019, also successfully demonstrated controlled solar sailing in Earth orbit. For interstellar travel, solar sails have limitations. As you move away from the sun, sunlight weakens. At Jupiter's distance, the Sun provides only 4% of the light available at Earth. At Pluto's distance, less than 0.1%. Beyond the solar system, solar sails become nearly useless. But what if we didn't rely on the Sun? What if we built a powerful laser on Earth or in orbit around the Sun and used it to illuminate the sail from behind, providing constant thrust even as the spacecraft travels deeper into interstellar space? This is the concept behind laser-pushed light sails, and it's the basis for the Breakthrough Starshot initiative. Breakthrough Starshot, announced in 2016 and funded by billionaire Yuri Milner, proposes building an array of powerful ground-based lasers. These lasers would focus on a tiny spacecraft, perhaps just a few grams, equipped with an ultra-thin reflective sail. The combined laser beam would accelerate the craft rapidly, pushing it to 15 to 20% the speed of light, within minutes. At that velocity, the spacecraft could reach Proxima Centauri in about 20 years. The entire mission, from launch to arrival, would fit within a human lifetime. Of course, this creates new challenges. A few grams can only carry miniaturized instruments, not humans. The spacecraft would be unmanned, probably equipped with a tiny camera, basic sensors, and a radio transmitter. It would fly past Proxima Centauri at incredible speed, snap photos, and transmit them back to Earth. The signal would take 4.24 years to arrive. Still, this represents genuine interstellar travel within a time frame humans can appreciate. And if the technology works for small probes, perhaps it could be scaled up. A human-carrying spacecraft would need to be much larger. Instead of grams, we're talking tons. Life support systems, radiation shielding, propulsion for maneuvering, habitats, food, water, air. The mass adds up quickly. Accelerating tons to 20% light speed requires enormous energy. The laser array would need to be proportionally more powerful, perhaps requiring gigawatts or even terawatts of continuous output. That's more power than most countries generate. And there's another problem: deceleration. A laser-pushed light sail accelerates rapidly, but has no way to slow down. Without braking, the spacecraft would shoot past its destination at 20% light speed, spending mere hours in the target star system before vanishing back into interstellar space. To stop, you'd need a second laser array at the destination, which obviously doesn't exist. Or you'd need to carry fuel for braking, which dramatically increases mass and reduces maximum speed. Or you'd need some clever orbital mechanics, perhaps using the target star's gravity to slow down, though that's extraordinarily difficult at relativistic speeds. Despite these challenges, laser-pushed sails remain one of the most promising propulsion concepts for reaching nearby stars within a human lifetime. With sufficient engineering development, we might be able to send small probes to Proxima Centauri by the end of this century. Larger vessels carrying humans might follow in the next century. We mentioned Project Orion earlier. Let's examine it more closely, because it remains one of the few propulsion concepts that could plausibly send humans to another star within a lifetime. The concept is straightforward. Detonate nuclear bombs behind your spacecraft. The explosion creates a brief but intense pulse of energy. A massive shock absorber plate catches this energy and converts it into forward motion. Repeat every few seconds, and you have a continuous acceleration. It sounds insane, and in many ways, it is. You're literally riding a controlled series of nuclear explosions. But the physics works. Calculations performed by physicists like Freeman Dyson in the 1960s showed that nuclear pulse propulsion could achieve exhaust velocities far exceeding chemical rockets. Depending on the design, an Orion-class spacecraft could reach 3 to 5% the speed of light. At 5% light speed, Proxima Centauri becomes reachable in 85 years. That's a single human lifetime. An Orion spacecraft would need to be massive. The shock absorber plate alone would weigh thousands of tons. You'd need hundreds or thousands of nuclear devices for the journey. The entire vessel might weigh 10,000 tons or more. But that mass includes substantial living space. Unlike tiny laser sail probes, an Orion vessel could carry hundreds of people in relative comfort. It would be a generation ship, but one where the same generation that launched might actually arrive. The political and environmental challenges are obvious. Launching nuclear devices into space violates international treaties. The fallout from ground launches would be unacceptable, and the risk of a catastrophic malfunction is significant. However, if the spacecraft was assembled in orbit and the nuclear pulse propulsion only activated far from Earth, the environmental impact could be minimized. Future generations might decide the benefits of interstellar travel outweigh the risks. A more advanced version called nuclear fusion pulse propulsion might be cleaner. Instead of fission bombs, you'd use fusion devices, which produce less radioactive fallout. Fusion also releases more energy per unit mass, allowing for higher speeds. With optimized fusion pulse propulsion, speeds approaching 10% light speed might be achievable. That would reduce the travel time to Proxima Centauri to about 42 years. Launch at age 20, arrive at age 62. Still old, but alive. This represents the outer limit of what's achievable with nuclear propulsion. Beyond 10% light speed, the engineering challenges become extreme, and you start encountering relativistic effects that complicate everything. Antimatter is the most energy-dense fuel possible. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy, according to Einstein's famous equation E=mc2. No other reaction is more efficient. For comparison, chemical reactions convert roughly E.01% of mass into energy. Nuclear fission converts about 0.1%. Nuclear fusion converts about 0.7%. Matter-antimatter annihilation converts 100%. This means a tiny amount of antimatter could propel a spacecraft to enormous speeds. 1 kilogram of antimatter, combined with 1 kilogram of matter, releases as much energy as a 43 megaton nuclear bomb. That's more energy than humanity uses in a year. Antimatter rockets could theoretically accelerate spacecraft to 50% the speed of light or more. At 50% light speed, you could reach Proxima Centauri in 8.5 years. Add time for acceleration and deceleration, and the trip might take 15-20 years total, entirely within a single human lifetime. But there's one enormous problem. We don't have antimatter. Antimatter exists. It's created in particle accelerators and in certain natural processes like lightning strikes and radioactive decay, but it's extremely rare and difficult to produce. CERN's Large Hadron Collider can produce tiny amounts of antimatter, measured in nanograms. Storing antimatter is even harder. The moment it touches normal matter, it annihilates. So it must be contained using magnetic fields, suspended in a vacuum, never touching any physical surface. The technology to do this exists, but is incredibly complex and energy-intensive. Producing enough antimatter for a spacecraft would require enormous energy input. Current production rates are about 1 nanogram per year at CERN. A realistic antimatter rocket might need kilograms of antimatter. At current rates, it would take billions of years to produce enough. Even if we dramatically improved production efficiency, antimatter remains fantastically expensive. Estimates suggest antimatter costs about $100 trillion per gram to produce. A kilogram would cost $100 quadrillion, far more than the entire global economy. So antimatter rockets, while theoretically amazing, are not practically feasible with anything resembling current or near-future technology. Perhaps in centuries to come, if we discover natural sources of antimatter or develop revolutionary production methods, antimatter propulsion might become viable. For now, it remains a theoretical limit, showing what's possible if we could somehow overcome the production and storage challenges. One major limitation of all the propulsion systems we've discussed is that they require carrying fuel. Even antimatter rockets need antimatter, which must be produced and stored before launch. But what if you could collect fuel along the way? Space isn't truly empty. Even in interstellar space, there's about 1 hydrogen atom per cubic centimeter. That's incredibly sparse, but if you had a large enough collector, you could gather hydrogen as you traveled. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, does exactly this. An enormous electromagnetic scoop, perhaps thousands of kilometers wide, funnels hydrogen into a fusion reactor. The reactor fuses hydrogen into helium, releasing energy. This energy propels the spacecraft forward, and the helium is expelled as exhaust. The beauty of this concept is that you never run out of fuel. As long as you're moving through space, you're collecting hydrogen. And since you're using that hydrogen for propulsion, you can keep accelerating continuously. In theory, a Bassard ramjet could accelerate to a significant fraction of light speed, perhaps 50% or more. And because it doesn't carry fuel, it could maintain that speed indefinitely. But the engineering challenges are staggering. The electromagnetic scoop would need to be enormous, far larger than anything humanity has ever built. The fusion reactor would need to operate continuously and efficiently, converting nearly all the collected hydrogen into thrust. And there's a more subtle problem. At very high speeds, the collected hydrogen doesn't just provide fuel, it also provides drag. The faster you're going, the more hydrogen you hit per second, and the more energy it takes to push through it. At some point, the drag equals the thrust, and you can't accelerate anymore. Calculations suggest the maximum speed for a Bassard ramjet might be around 12% the speed of light due to this drag limitation. That's still fast enough to reach Proxima Centauri in about 35 years, but not as fast as optimistic early estimates suggested. Moreover, we haven't achieved controlled fusion yet, even in stationary reactors on Earth. Building a fusion reactor that works efficiently in space, on a moving spacecraft, using hydrogen scooped from interstellar space, is far beyond our current capabilities. The Bassard ramjet remains an elegant concept, a theoretical possibility that might become practical in the distant future. But for now, it's not something we can build or test. Now we enter the realm of physics that seems like science fiction, but is actually proven, tested, and fundamental to how the universe works. We're going to talk about what happens when you travel at speeds approaching the speed of light. Einstein's special theory of relativity, published in 1905, revealed something remarkable. Time is not absolute. Time passes at different rates for observers moving at different speeds. The faster you move, the slower time passes for you relative to someone stationary. This is called time dilation, and it's not a theory or hypothesis. It's been measured countless times. Atomic clocks flown on airplanes run slightly slower than atomic clocks left on the ground. GPS satellites must account for relativistic effects, or their positioning would drift by miles per day. At everyday speeds, time dilation is negligible. If you drive at 60 miles per hour for an hour, you age about 0.1 seconds less than someone standing still. You'd never notice. But at speeds approaching the speed of light, time dilation becomes dramatic. Let's use an example. Imagine you board a spacecraft that can accelerate continuously at 1g, which is Earth's gravity. That's comfortable for humans. No special training needed. You stand on the floor of the ship as if you were on Earth. Your spacecraft accelerates at 1g, continuously for years. Relative to people on Earth, you're going faster and faster. But you don't feel anything unusual. Inside your ship, time passes normally. You age at the normal rate. Everything feels fine. However, from Earth's perspective, something strange is happening. As your velocity increases, time aboard your ship slows down. You're aging more slowly than people on Earth, and distances in your direction of travel contract, appearing shorter to you than to stationary observers. After 1 year of constant 1g acceleration from your perspective, you're moving at about 77% the speed of light relative to Earth. After 2 years, 97%. After 3 years, 99.4%. You approach the speed of light asymptotically, getting closer and closer, but never quite reaching it. According to special relativity, nothing with mass can reach the speed of light. As you approach light speed, your mass effectively increases, requiring more and more energy to accelerate further. It would take infinite energy to reach exactly the speed of light, which is impossible, but you can get very close. And when you do, time dilation becomes extreme. If you maintain 1g acceleration for long enough, reaching 99.99999% the speed of light, time for you slows dramatically relative to Earth. 1 year for you might equal hundreds or thousands of years on Earth. This creates a strange possibility. From your perspective, time passes normally. But from Earth's perspective, you're living in slow motion. You could travel enormous distances while experiencing only moderate passage of time. Let's calculate a specific example. Suppose you want to reach the center of our galaxy, the Milky Way. That's about 26,000 light years from Earth. At conventional speeds, it would take at least 26,000 years to get there, and you'd die long before arrival. But if you accelerate at 1g for the first half of the journey, then decelerate at 1g for the second half, something remarkable happens. From Earth's perspective, the journey takes about 26,000 years. But from your perspective, aboard the ship, the journey takes only about 20 years. 20 years. That's within a human lifetime. You'd age 20 years while crossing 26,000 light years. You could leave Earth in your 20s and arrive at the galactic center in your 40s. Of course, everyone you knew on Earth would be dead. Millennia would have passed. Civilizations would have risen and fallen. But you, subjectively, only experienced 20 years. This is the strange gift of time dilation. It allows for relativistic travel across vast distances within a single human lifetime, from the traveler's perspective. Let's push this further. Suppose you want to reach Andromeda, the nearest large galaxy to the Milky Way. Andromeda is 2.5 million light years away. With continuous 1g acceleration and deceleration, the journey from your perspective would take about 28 years. You'd age 28 years while crossing 2.5 million light years. On Earth, 2.5 million years would pass. Your species might not even exist anymore when you arrive, but you'd be alive, having experienced less than 3 decades of travel. In principle, you could travel anywhere in the observable universe within a single human lifetime, from your perspective, if you could maintain 1g acceleration for long enough. Want to reach a quasar 10 billion light years away? It would take about 35 years of ship time with continuous 1g acceleration and deceleration. On Earth, 10 billion years would pass. The sun would be long dead, the galaxy unrecognizable. But you'd arrive, having aged only 35 years. This sounds like a loophole in the cosmic speed limit. And in a sense it is. You're not breaking the laws of physics. You're not exceeding the speed of light. But from your frame of reference, you're effectively traveling faster than light. However, there are problems, enormous fundamental problems that prevent us from actually doing this. First, the energy requirements. Accelerating a spacecraft to near light speed requires staggering amounts of energy. Even a small spacecraft, just a few tons, would need energy equivalent to multiple years of total human civilization's energy output. There's no known propulsion system that could provide continuous 1g acceleration for years while carrying humans. You'd need an impossibly efficient energy source and reaction mass to throw backward. Antimatter would work, theoretically. But as we discussed, we can't produce enough antimatter. A perfect fusion reactor might work, but we haven't built one yet. Anything less would run out of fuel long before reaching relativistic speeds. Second, there's the problem of interstellar medium. Space isn't perfectly empty. Even in the voids, between stars, there are occasional atoms. At normal speeds, these atoms are harmless. But at 99% the speed of light, each hydrogen atom hits your spacecraft with the energy of a cosmic ray. At 99.99999% light speed, hydrogen atoms become deadly radiation. Your hull, no matter how thick, would gradually erode. Crew would be exposed to radiation doses that would kill them quickly. You'd need enormous amounts of shielding, which increases mass, which requires more energy to accelerate, creating a vicious cycle. Or you'd need some kind of electromagnetic deflector shield that pushes particles away before they hit the hull. We don't have that technology. Third, there's the existential problem. If you travel to a destination thousands of years in Earth's future, you can never return to your own time. The Earth you left will be gone. Everyone you knew will be dead for millennia. You'd arrive as a stranger from the past, in a universe that's moved on without you. For many people, this would be emotionally unbearable. The isolation would be absolute. You could never go home. You'd be permanently cut off from your civilization, your culture, your history. And yet, despite these challenges, relativistic travel remains theoretically possible. The laws of physics allow it. Time dilation is real. If we solve the engineering problems, propulsion, energy, shielding, humans could travel across the galaxy, or even to nearby galaxy clusters within a single lifetime, from the traveler's perspective. This represents the ultimate limit of how far humans could travel, not limited by distance, but limited by time dilation and engineering constraints. In practice, with foreseeable technology, humans could probably travel a few dozen light-years within a lifetime. Reaching Proxima Centauri in 10 to 20 years seems feasible with advanced propulsion. Reaching stars 50, 100 light-years away might take a lifetime, but remains possible. Beyond that, we're talking about technologies that don't yet exist and might not be buildable for centuries, but the physics allows it. And that's a remarkable thought. So far, we've focused on propulsion, on going faster. But there's another approach. Don't go faster, just live longer. Or more precisely, don't require the original crew to complete the journey. Generation ships represent a different philosophy of interstellar travel. Instead of racing to the destination at high speed, you build a massive spacecraft, essentially a small, self-contained world, and travel at modest speeds for centuries or millennia. The crew that launches knows they'll never see the destination. They're traveling for their children, or their children's children, or descendants many generations removed. The journey becomes a way of life, and arrival is something future generations will experience. This concept has been explored extensively in science fiction, but it's also been seriously studied by scientists and engineers. In the 1970s, NASA commissioned studies of generation ships, examining their feasibility. A generation ship needs to support human life indefinitely. That means closed-loop life support, recycling air, water, and waste, agriculture to grow food, medical facilities for healthcare, education systems for children, social structures to maintain order and purpose. It also means sufficient population to avoid genetic bottlenecks and inbreeding. You'd probably need at least 500 to 1,000 people initially, and mechanisms to ensure genetic diversity across generations. The size of such a vessel would be enormous. Not a spacecraft in the conventional sense, but more like a small city or large town enclosed in a hull. It might be built from a hollowed asteroid, rotated to provide artificial gravity through centripetal force. Or it might be constructed as a cylinder, like the O'Neill cylinder concepts proposed for space colonies. A cylinder 5 miles long and 2 miles in diameter could house tens of thousands of people, with ample room for agriculture, parks, and living space. Traveling at modest speeds, say 10% the speed of light, such a vessel could reach Proxima Centauri in about 42 years. That's fast enough that some of the original crew might survive to see arrival, though most would die along the way. For more distant stars, the journey would span multiple generations. A trip to a star 50 light-years away at 10% light speed would take 500 years. That's perhaps 20 generations of humans born, living, and dying aboard the ship. This creates profound psychological and social challenges. How do you maintain motivation across generations for a goal none of them will personally achieve? How do you prevent social collapse, mutiny, or loss of mission focus? There's also the question of whether it's ethical to commit unborn generations to life aboard a spacecraft. They didn't choose this journey. They're born into a world not of their making, traveling to a destination they might not want to reach. These philosophical questions aside, generation ships are technically feasible. We could, with current or near-future technology, build a large rotating habitat equip it with nuclear reactors for power, stock it with supplies and genetic material, and send it toward a nearby star. The journey would be slow. The crew would age and die. But humanity would reach another star system, and that might be worth the sacrifice. However, there's a darker possibility. What if technology advances during the centuries-long journey? A ship that launched in 2100, expecting to take 500 years to reach its destination, might be overtaken by a faster ship launched in 2300 that arrives first. The original crew, or their descendants, would arrive to find the destination already colonized by later travelers who,